Okay, in this lecture, we're going to be discussing section 4.4, which is mass and weight. So the weight of an object is the gravitational force exerted on it by the Earth or whatever other object exerts the force. Weight is a force and is therefore a vector quantity. The magnitude of the weight of an object in any specific location is equal to the product of the mass and the magnitude of the acceleration due to gravity. The weight of an object depends on its location, but the mass is independent of location. It exists no matter what proximity the other body is to it. That mass is always going to be there. So an object's weight depends on its mass and on its acceleration due to gravity at its location. So mass characterizes the inertial property of an object. In other words, the propensity of an object to maintain its velocity. The greater the mass, the greater the force is needed to cause a given acceleration. This meaning is reflected in Newton's second law. Weight, on the other hand, is a force exerted on an object by the gravitational pull of the Earth or some other astronomical body. Everyday experience shows us that objects that have large mass also have large weight. So a cart loaded with bricks is hard to get started rolling because of its large mass. And it is also hard to lift off the ground because of its large weight. On the moon, the cart would be just as hard to get rolling because it would be easier to lift. So what exactly is the relationship between mass and weight? So you can see here, mass of m, you've got the resultant force this way, and so you've got the acceleration. Here, you've got the mass, you've got the weight pulling down because the acceleration is in this direction. So, a free-falling object has an acceleration with magnitude equal to g. In other words, the acceleration due to gravity. Because of Newton's second law, this acceleration requires a force. If a 1 kilogram object falls with an acceleration of magnitude 9.8 meters per second, the force required must have a magnitude of 9.8 newtons. But the force that makes the object accelerate downwards is the gravitational pull of the Earth. In other words, the weight of the object. Any object near the surface of the Earth that has a mass of 1 kilogram must have a weight with magnitude 9.8 newtons in order for it to have the acceleration we observe when it's in free fall. Or more generally, the force that the Earth applies to an object is proportional to its mass and also proportional to the gravitational constant. If you write it with vector components, it's going to, instead of just being mass times gravity, it's going to be minus mass times gravity. And of course, the weight has units of newtons. So we're going to use the value of g equal to 9.80 meters per second squared for problems related to the Earth. The value actually varies on the Earth's surface depending on where you are. It's not a perfect sphere, and because of the effects due to rotation, orbital motion, and composition, it's going to change. So at a point where gravity is equal to 9.80 meters per second squared, the weight of a standard kilogram is 9.80 newtons. At a different point where the acceleration is a little bit less, then the weight's going to be a little bit less. But the mass is still going to be 1 kilogram. And the weight of an object varies from one location to the other, but the mass does not. If you take a standard kilogram to the surface of the moon, where the acceleration of free fall is a fraction of what it is here on Earth, then the standard kilogram is going to be 1.62 newtons, but the mass is still 1 kilogram. So you can see the diagrams there. So here's another useful fact. An object with a mass of 1 kilogram has a weight of about 2.2 pounds at the Earth's surface. In the British system, the unit of force is the pound or pound force. And the unit of mass is the slug. The unit of acceleration is 1 foot per second squared. So 1 pound is equal to 1 slug times feet per second squared. In the CGS metric system, the unit of mass is the gram. which is equal to 10 to the minus third kilograms. And the unit of distance is a centimeter. The corresponding unit of force is called the dyne. One dyne is equal to 1 gram times 1 centimeter per second squared, or 10 to the minus fifth newtons. And it's important to understand that the weight of an object acts on the object all the time, whether it's in free fall or not. When a 10-kilogram flower pot hangs suspended from the chain, it's in equilibrium and its acceleration is 0. But its 98 Newton weight is still pulling down on it. In the case where the chain pulls up, in this case, the chain pulls up in the pot, applying a 98 Newton upward force. And so the vector sum of the two 98 Newton forces is 0, and so the pot's going nowhere. So here are some more exercises for you to go through.